Eureka!
The story so far. The tendency things have to keep on doing what they're already doing is called inertia. Mass is a measure of inertia. But in order to make a thing change what it's doing, you have to use force. And force varies not only with mass, but also with change of speed. And now, acceleration, part 1. If you wanted to exert as little force as possible, which of these two bikes would you choose to ride? No contest. The modern racing bike has much less mass than the old-fashioned bike, and therefore much less inertia. So you'll need less force to make it move. But wait, is that all that force is proportional to? To mass? Isn't there something else? Yes, change of speed. Mustn't forget that. Force is also proportional to change of speed. If you want to reduce the force you put into pedaling, you're better to go from 0 to 25 kilometers an hour than to try to zoom up to 50 kilometers an hour. Too easy, you think? Well, go on then. Ride the bike at 25 kilometers an hour. Stop. That wasn't 25 kilometers an hour. You weren't even doing 5 kilometers an hour. That's right. It takes time to reach the speed you want to go at. In the first second you start pedaling, you'll be lucky to get up to 3 kilometers an hour. After the second, you may reach 6. After the third second, 9, and so on. It'll probably take you 8 seconds or so to reach 25 kilometers an hour. Let's look at that again. That's it. Now you're going at your top speed. Is this when you're exerting maximum force? You think so? Well, take your feet off the pedals then. You're hardly losing any speed at all, are you? You're exerting 0 force, and yet if it weren't for the bumpiness of the road and the wind resistance slowing you down, you'd still be going at 25 kilometers an hour. Why? Because of the first rule of physics. Things like to keep on doing what they're already doing. It isn't the speed of 25 kilometers an hour itself that requires effort or force from you. It's getting up to that speed. That's why we say that force varies with mass and change of speed. But the more quickly you change your speed, the more force you'll have to exert. If making your bike go from 0 to 25 kilometers an hour in 8 seconds requires 1 unit of force, then making it go from 0 to 25 kilometers an hour in half that time, in 4 seconds, will require 2 units of force. The thing is, we're not just talking about change of speed, but about an increase of speed in a certain time. In other words, we're talking about rate of change of speed. So we should say that force varies with mass and rate of change of speed. But that's a very long sentence, so we shorten it by using the other word for rate of change of speed: acceleration. Force varies with mass and acceleration. And we can shorten that still further by turning it into an equation. Force equals mass times acceleration, which just so happens to be the second rule of physics. This should be obvious to cyclists, and even more obvious to motorists, who are always going on about acceleration. But what about a baseball pitcher? Does he need time to get the ball up to its top speed? All right. Pitch that ball at 50 kilometers an hour. Freeze. It isn't going at 50 kilometers an hour at this point. More like 10 kilometers an hour. This is just the beginning of your wind-up. A bit later, the ball may reach 20 kilometers an hour, then 30, then 40. But it's only at the last split second as it leaves your hand that it reaches its top speed. The fact is, you don't so much pitch a ball at 50 kilometers an hour as accelerate it up to 50 kilometers an hour. That's what your wind-up is for. You may call yourself a baseball pitcher if you wish, but in reality, you're a baseball accelerator.
Eureka!
The story so far. The greater the rate of change of speed, the greater the force required. Another word for rate of change of speed is acceleration. The more you accelerate, the more force you need. But force also varies with mass. So we say that force equals mass times acceleration. And now, acceleration, part 2. How do we measure acceleration? That's one way. But there's a better method. You see, most things do all the accelerating they're going to do in a matter of a few seconds. So it isn't very practicable to measure their increases in speed in kilometers per hour. Take this locomotive, for instance. It's a very old steam engine, and it can only do 36 kilometers an hour. But its acceleration is surprisingly good. It can get up to this speed in only 10 seconds. Yes, it is impressive. But can you answer this? How far will it have gone by the end of the first second? Or by the end of 10 seconds? Give up? That's what comes of mixing speed in kilometers per hour with time in seconds. We've got to reduce it all to seconds, and we'd better reduce the kilometers to meters as well while we're at it. The train's top speed is 36 kilometers an hour, which is the same as 36,000 meters in an hour. Since an hour contains 60 minutes, we can divide 36,000 meters by 60 to find out how many meters it goes in 1 minute. Then we divide again by 60 to see how many meters it'll go in 1 second, which comes to 10 meters in 1 second. So we now know that 36 kilometers per hour is the same as 10 meters per second. That means that once the locomotive has reached its top speed, it is covering exactly 10 meters of track every second that goes by, never less and never more. But remember, this is speed, not acceleration. Acceleration means that with every second that passes, the train advances an increasing number of meters until it's eventually moving at a speed of 10 meters per second. But it didn't start out that way. Ready? You've got 10 seconds in which to attain a speed of 10 meters per second. Very good. Now, let's replay that and analyze what happens. In the first second, you reach a speed of 1 meter per second and cover a small amount of railroad track. In the second second, you reach a speed of 2 meters per second and cover a larger amount of track. In the third second, you're going at 3 meters per second and covering yet a longer stretch of track, and so on until by the end of the 10th second, you're going at a steady speed of 10 meters per second and covering 10 meters of track during every second that passes from then on. Your acceleration is over. But how much was that acceleration exactly? That's right. Your locomotive increased its speed by 1 meter per second, every second. In other words, your acceleration was 1 meter per second, which physicists like to write like this. And that's how you measure acceleration.